All right, everyone. Hello, Professor Brian Macon here. Welcome back to another calculus video. Welcome back to the Calculus Fun Room. And in this section, in this video, we're going to talk about one of the many applications of integration, and we're going to calculate arc length. So the basic idea here being that we want to find the length of a curve. So, I'm a visual learner. I want to look at this visually, right? And so let's say that we're looking at the length of a curve. Let's say we have this Word document never listens to me. All right. One of these days, it will listen to me. So let's say we have a XY grid. We're in the Cartesian plane. And we're looking at some curve, right? So we have some function y equals f of x, whatever that function might be, y equals x squared, y equals sine x in general, y equals f of x, and we want to find the length of that curve. So in a construction type of manner, what we could do, let's say we had engineering paper, it's a gridded graph paper, and we draw the curve quite precisely, and then we take a piece of yarn, and we lay the yarn down on top of the curve, and then we pull the yarn off. We hold it straight, right? We kind of hold it taut, and then we put it on a ruler and we measure it. But we're in calculus, right? So we want to develop a more precise manner in which we can do this. So this is actually a pretty simple concept, and I'm going to try to exaggerate a couple of things here. So to approximate the length of the curve, right, typically what we would do is, let's say, break the curve into line segments. So for example, let's say I pick this curve, and this point and this point on the curve, and I approximate the curve with that line segment. So you can see that's not the best approximation, but then the next 2 points is a pretty decent approximation. And then the next 2 points, pretty good approximation. Then I'm going to try and exaggerate a little bit, right? Here's another line segment approximating the curve. And then we have, let's say, this line segment and this line segment. So what do I have there? 1, 2, 3, 4, 5. I have 6 line segments. But keep in mind, our typical calculus approach is we want to get a better approximation, so we might use 10 line segments. And then we want an even better approximation, we might use 20 line segments. And then we want an even better approximation, we might use 50 line segments, and 100 line segments, and 500, and 1,000. And so we're doing a limit process. And before we get to that limit, let's think about what the length of each of these line segments are, right? So the length of this first line segment estimates the length of the curve. And again, it's not the best estimation over that segment. But then the distance between the points on the next line segment is a pretty good estimator to the length of the curve. Now again, the more and more line segments we use, the better the approximation is going to be, right? So for example, if I squeeze a line segment in here, that's a better approximation. There's a better approximation. So let's say each of these, right, I put twice as many line segments, right? So on and so forth. So again, there's that limit process. We're going to look at 6 line segments, 10, 20, 50, 100. So the length of any line segment is the distance formula, right? The distance between any 2 points, right? Let's say the distance from point 1 to point 2 is going to be the distance formula. So it'd have the square root of, right? So we have the difference in the x's squared plus the difference in the y squared. So usually in an algebra class, you develop the distance formula. Keep in mind that's really Pythagorean's theorem. If we think about this line segment here, technically being the hypotenuse of a right triangle, right? We have a squared plus b squared equals c squared, and so c is the square root of a squared plus b squared. So we have the difference in the x's, difference in the y's, and we can get a little bit more precise. We could call this, delta x squared plus delta y squared. All right, now remember we're going to do this for each line segment. So, in the original sketch, I said there were 6 line segments. And then cutting those in half, I got 12 line segments, right? So typically in a calculus textbook, what we do is we look at, symbolically the ith line segment, right? So the length of this curve, let me say, is approximately, the length of this curve is approximately the sum of all of those distances, so the length of every line segment. So let's call it delta x sub I squared plus delta y sub I squared. Okay, so again, this is representing the length of the ith line segment. So let's say, we go from 1 to n. And I'm being a little loose here mathematically. I'm just having a conversation with you to discuss where the formula comes from. Now again, if I'm summing from 1 to 6, there's the length of my 6 line segments. And if I sum from 1 to 50, right, there's the sum of 50 line segments. Right? So again, we're going to have a limit process that we involve here. And we're going to let the number of rectangles become infinite. The number of line segments become infinite. So the length will exactly equal the limit as n goes to infinity of that summation, which roughly looks something like this. So here we have the distance formula, the length of every line segment. We're summing up those infinitely many line segments. Now, something I just want to point out to you here, let me back up for a second. If we come back to this graph, think about this for a moment. Let's say the distance between these 2 points are between this x value. So here's the second x value, here's the first x value, let's say, right? And then the distance between this one and this one that I originally drew. So our delta x is what we're talking about there, right? I mean, we have a delta y in this formula as well, right? But let's look at the delta x momentarily. So when we developed integrals as an area under a curve, right, the delta x was like the part of the rectangle, right? We had a rectangle that we would draw here. That's not what we're looking at in this case. We're looking at lengths of line segments. But think about this for a moment. As I squeeze more and more line segments in here, this delta x is going to get smaller, right? So when I cut this between here, right, here was a line segment, that delta x is half of the prior delta x, right? So as n goes to infinity, my delta x gets smaller and smaller and smaller and goes to 0. So what you will see sometimes in the symbolization, depending on the calculus book you look at, they might say delta x goes to 0. Either one, they both represent the same concept conceptually. Now, so back in the Calc 1 class, what we would call this is a Riemann sum. So we have a summation. This is a Riemann sum, and the Riemann sum, being the limit as n goes to infinity. Now, if I stick with what I have here, this isn't the formula you would see in any textbook, but if I stick what I have here, remember that the limit of the Riemann sum produces an integral, right? We represented the summation as a Riemann sum as an integral, right? And then, all right, technically, remember a small change in x, we symbolically wrote as a dx, right? And then a small change in y, we symbolically would write as like a dy. Okay? So technically, here's my formula, but this formula isn't really useful the way that it sits. So what we will typically do is a little bit of algebra simplification. Now, technically, to be a little bit mathematically rigorous, we don't jump to this last line right away. What we do is some algebra with the delta x terms. So what I want to do is let's just come over here and let's do a little bit of algebra on that expression. So I'm going to come back for a second and let's just look at this for a moment. And we have delta x squared plus delta y squared. And we're going to do a little bit of algebra cleanup there, and it's going to give us something that's much more useful symbolically, right? So let's say underneath the radical I factor out the delta x squared. So I factor out the delta x squared, right? So what does that do? Well, it leaves me with a 1 right here, right? So that when I distribute, delta x squared times 1 is the delta x squared, and then when I factor out the delta x squared from the other term, it leaves me with this expression. Right? Oops, that's a delta x in the denominator, right? So when I distribute this delta x squared back in, those cancel, and I just get the delta y squared that we had there. Right? So algebraically, I factor out the delta x squared, and I'm at this point. And then I have those parentheses, right? So then the advantage to this is what I have over here is delta y over delta x. So I'm going to do two things here algebraically. The square root of delta x squared. So I have the square root of 1 plus, and I'm going to write delta y over delta x quantity squared. So algebraically, that's totally legal. I'm going to use the property of exponents to write it in this manner. And then I have times the square root of delta x squared. So now, if we were to take a limit, right, in the limit as delta x goes to 0, right, as delta x goes to 0, this becomes 1 plus, we get the derivative dy dx squared, and then the radical and the square go away here, and we get just the dx. So in our limit process, this is really what we want to write. So I'm going to scroll back up for just a second. So this expression that we have right here in green, right, this expression is really what we're going to write from what we got down there. So we're going to have the integral of 1 plus dy dx squared. Right? So the length becomes, let me go back to like a different color here. So the length is the integral of the square root of 1 plus the derivative of the function squared dx. Right? Now, keep in mind we're going to have limits of integration here. Right? So in other words, we're going to be looking at the length of some curve over, some interval a to b. Right? All right, so we have a finite piece of curve. We're going to find the length of that finite piece of curve. And so there's our formula for arc length. Now eventually we're going to develop multiple applications of integrals, right? And this is one of them. So an integral can be used to calculate the area under a curve. And we actually, in a prior video, we found the volume of rotation for a curve to be an integral. So we could use an integral to evaluate volume. And we also found areas between curves using an integral. So here's another application of integrals. Integrals can also be used to calculate arc length. And then, this conversation we just had illustrates the beauty of the limit process. Right? So the beauty of the limit process is we can approximate a measurement, and then through a limit, we can get an exact measurement. And we've done that all through this class. The limit process has been such a wonderful tool. We estimated tangent lines by using a secant line, and we let delta x go to 0. And that's what created the derivative, the dy dx, the rate of change, which is a derivative. So we've been using limits throughout this entire course, Calc 1 and Calc 2. Beautiful tool to allow us to take an approximation to an exact measurement. So let's take a look at an example where we apply this. All right, so in this example, let's say we want to find the length of y squared equals x cubed from 1, 1 to 4, 8. So just to get a visualization of this, I don't really want to have to, plot points and sketch this graph. So I'm going to go to desmos.com, and I'm going to start graphing. And I'm going to type in y squared equals x cubed. All right, so I'm going to say y raised to the second equals x raised to the third power. And there's the graph. Right? Now technically I want to go from 1, 1. So here's 1, 1. And then 4, 8. So here's 4, 8 right here. So that's what I'm looking at. I'm looking at this curve. And I don't want to really look at the bottom half of the curve. So I'm going to look at y squared equals x cubed from 1, 1 to 4, 8. So visually speaking, we are looking at, where did my problem go? This Word document. likes to play games with me. All right, so we have, let me stick with blue for my axes. Right? So we had something that looked roughly something like this. Right? We had this guy. Right? And we're going to go from 1, 1 to, let's say, 4, 8, roughly right there. Right? So we know that our integral formula, the length, is the integral of the square root of 1 plus dy dx squared dx from a to b. Right? Now, in order to use the formula the way that we're writing it here, we need to find the derivative. So we have y squared equals x cubed, which then I'm going to, square root both sides, or I'm going to raise both sides to the 1/2 power. Right, so if I raise the left-hand side to the 1/2 power and I raise the right-hand side to the 1/2 power, we're going to get y equals x to the 3/2. So now we could take the derivative, so we would have dy dx, and then we're just going to use the power rule here, right? So I'm going to bring the power down, and I'm going to take 1 away from the power. So there's my derivative. That is supposed to be a 2 down there. So there's my derivative. So I'm going to plug that derivative right here into my formula and then square it. So we have our arc length being the integral of the square root of 1 plus, and then we have our dy dx that's going to get squared. Now, when we look at this graph, the x limits of integration go from 1, that's a 1, right, to 4. So those are going to be my x limits of integration from 1 to 4, right? And, remember, kind of mentally speaking, right, the dx indicates my integrals in terms of x, right? And then I need my x limits of integration from 1 to 4. And there's this setup of finding the arc length. So we could evaluate this integral, right? If we follow this all the way through, I get the square root of 1 plus, and this is what? This is 9/4, and then x to the 1/2 squared is just x dx, and we're going from 1 to 4. So in this case, so remember back in the prior chapter, right, we talked about techniques of integration, and if I had a square root, a lot of times we used trigonometric substitution. Right? We drew a triangle, we labeled the triangle, and we used trig functions to substitute for variables. Now that was typically only the case when I had something, let's say, quadratic. Those are usually the forms that we would see in the homework. So if I had like 1 plus x squared, right, that would be a trig sub. But in this case, it's linear. So I'm going to do a u substitution. I'm going to let u be the 1 plus 9/4 x, and then our du dx is just 9/4. So our du is 9/4 dx. Or in other words, our dx is 4/9 du. So I'm going to plug all of this stuff in, right? So I have the square root of u, and then my dx is 4/9 du. There's my integral. Okay. Now we could, if we wanted to, I'll go ahead and convert, right? We could convert the limits of integration, right? So if x is equal to 1, what's my u? So I'd have 1 plus 9/4 times 1. 1 plus 9/4. So I have 4/4 plus 9/4, which is 13/4. So there's my u limit of integration. And then if x is 4, the 4's cancel. I get 1 plus 9, which is 10. So there's my u limits of integration. So again, just to see this integral all the way through, this is really u to the 1/2, right? So I have a 4/9. I'm going to pull out of my integral, and I got u to the 1/2. So this is going to be 4/9. So I'm going to add 1 to the power. So I get u to the 3/2 and then multiply by the reciprocal. And then we're going to evaluate from 13/4 to 10. So there would be my antiderivative. Right? And then I could do a little bit of simplification here, right? 2 times 4 is 8, 3 times 9 is 27. So I got 8 27ths, and then I have, 10 to the 3 halves minus 13 fourths to the 3 halves. All right, so let's say we go ahead and finish off this arithmetic. So, remember properties of exponents. If we have a rational exponent, right, let's say we have x to the 3 halves, what we could do is we could write that as the square root of x cubed, or we could write that as the square root of x cubed. So what I'm going to do in this case is I'm going to pick this first one. Right, and the advantage to the first one is, think about this for a second. What I could do is the square root of x cubed. The root of x cubed I could write as the square root of x squared times the square root of x. So I get just x times root x. So if I plug 10 into this expression, 10 to the 3 halves is the square root of 10 cubed. So then we have 10 squared times root 10. Right? So, square root of 10 squared, which is just 10, and then root 10 inside. So I have 8 27ths, and this is just going to be 10 root 10 minus, and then this guy is going to be, 13 fourths root of 13 fourths. So there's my exact value. And if I take out a calculator and approximate that, let me pause the video real quick and plug this in my calculator. Okay, so what I did real quick is I used the integral function on my calculator, right? So on a TI, or just to remind you, what is it? Second math takes me to just math takes me to function integrator. So if I use function integrator, I type in square root of 1 plus dy dx squared from 1 to 4, and I get a decimal value of 7.633705416. And then if I let me call up the last thing I did here. So here was my answer as a fraction. So this was me typing everything in that we had here in the Word document right here. Here's this guy. And when I hit enter, we get the same decimal value, right? So our exact value matches the value, the integral that the calculator would give me. So here's an example of evaluating an integral to find arc length. Now, usually in a conversation like this within a calculus textbook, they add on a little bit of an additional conversation. And here's what the conversation would be. Right? So let's say that we scroll back up here for a second. Now in this example, what we posed was the equation y squared equals x cubed. Right? So what you'll see in your homework, sometimes, right, this was an implicit equation, right? But let's say we cover up the y squared, and we just have y equals x cubed. So if we have y equals x cubed, then we're going to find dy dx. So let me come down here and draw this picture for you for just a second, right? Or let's write out what I'm proposing to you. Right? So let's suppose you're given y equals a function of x. Then what we're going to find, right? So let's say y equals x cubed is an example, right? So then what we're going to do is we're going to find dy dx, which in this example was 3x squared. And then we're going to plug into the integral. Right? So we're going to do square root of 1 plus dy dx squared. Right? And then we're going to use x limits of integration here. Now in theory, we could have x as a function of y. So back in that example, let me scroll back up real quick. Let me stop where I just wrote. Right? Let me scroll back up real quick. And let's suppose for this example, we had written instead of y equals x to the 3 halves, right? In this example, we solved for y right here, y equals x to the 3 halves, and we took the derivative, dy dx. Now what we could have done is solved for x. We could have said x equals y to the 2/3, and we could have found dx dy. So usually what you see in a calculus textbook is they'll present both conversations to you, both conversations. So if we're given x equals a function of y, again, let's say, just real quick, let's say we had x equals y squared, right? Then what we would do is we would find dx dy, and we would use this version of the formula. Right, this version of the formula gives me y as my variable, right? So again, you could see dx dy would be 2y. So I'm going to have 2y squared as my derivative. So the variable is y, and I'm going to need y limits of integration on my integral. So you might be asking, how could I use this alternate version? And if we come back up to that page where we were doing the algebra simplification, so right here, remember we had the integral of delta x squared plus delta y squared. Right, that was my distance formula for each of the line segments. And what we did algebraically was we took the delta x squared and we factored it out. So we factored out delta x squared here. And what that did for me is that gave me a delta y over delta x squared, right? So we were here algebraically, 1 plus delta y over delta x squared, and then we ended up with a dx outside the integral. So my y is a function of x, and therefore dy dx, right? X is my independent variable. Here's my dx. And what we could have done at this point is instead of factoring out the delta x squared, we could factor out the delta y squared. So if we factor the delta y squared out, what we end up with here is a delta y squared. And then we have a 1. I mean, technically it's going to be 1 plus delta x over delta y squared, right? So again, right, if I factor out a delta y squared here, I'm left with a 1 on this term, and then this would be a delta x over delta y squared, and that's what we end up with. And then the root of delta y squared is going to be a delta y. So we're going to basically get the root of, right, 1 plus dx dy squared dy, right, because I have this dy here. So we can actually use the distance formula with some algebraic cleanup one way or the other. So if I have y as a function of x, like y equals x cubed, then I can just find dy dx and use this version of the arc length, right? This version of the distance. But if I have x equals a function of y, like x equals y squared, then we could find dx dy, which we would then plug into this form. I didn't write this down, right? Dx dy for this example would just be 2y, right? So I could use either one. So how do I know which one to use? Good question. So typically in a homework problem in a textbook, you would be given, let's say, y equals x cubed. And so they're kind of pushing you down the path to use this version, 1 plus dy dx squared. They might give you the equation x equals sine of y. Right? So if they give you x as a function of y, then they're kind of pushing you down that path. And either one of these versions of the formula gives me the length of the curve. Now in my example that we first started with, I gave you y squared equals x cubed. And so the version, the formula we had written at that point was the dy dx squared. So when I gave you the y squared equals x cubed, this was the only version of the formula that we had written at that point. So since we had y squared equals x cubed, we came down here and we solved for the y equation, right? We solved for y in my implicit equation, and then we took its derivative. But what we could have done is solve for x in that equation. You know what? So let's do that. Let's see that we would get the same arc length. So let's revisit our example. Let's revisit the y squared equals x cubed from 1, 1, 2, 4, 8. Okay. So this time, let's use the integral of square root of 1 plus dx dy squared. Okay. Now, again, for this equation, we weren't explicitly given x as a function of y, but we could easily solve for x, right? So we have x cubed equals y squared, right? I'm going to 1/3 both sides of the equation, so I'm going to get x equals y to the 2/3, and then I'm going to find dx dy. So I'm going to bring the power down, and I'm going to take 1 away from the power, right? So bring the 2/3 down, and then 2/3 minus 1, 2/3 minus 3/3 is negative 1/3. So there's my dx dy. So I'm going to plug into my integral, and what do we get? So we get the length being the integral of square root of 1 plus. So now my dx dy is 2/3 y to the minus 1/3. And I have to square that derivative. All right, so again, when I look at this integral, there's a sloppy 2 there, this tells me the variable is y. So I'm thinking of my independent variable as y, and we can see our integral is in terms of y. So I need y limits of integration on my integral. So when I look at my 2 points here, my y limits of integration are 1 to 8. So I'm going to have to put 1 to 8 on my y limits of integration for that integral. Now, this is the same length. We're looking at the same equation. We're looking at the same graph, the same curve from 1, 1 to 4, 8. So the prior integral that we did should numerically have the same exact value as the one we did the first time. So I'm going to pause the video real quick and type this in my calculator. I'll be right back. All right, so coming back at you. Here is my integral that we just evaluated, right? Let me slide this down. Let me see if I can get my Word doc, right? So here's my integral that we plugged into with the y variable. So here's me plugging into my calculator, right? So just keep in mind, I'm in function mode, right? So when I go to the mode key, I'm in function mode. So it's going to use the x variable when I type my variable button. So whatever, whether this is x or y, what we have here is the square root of 1 plus 2/3 the variable to the minus 1/3. So I have 1 plus 2/3 the variable to the minus 1/3, and all of that is squared. I'm squaring that derivative. And again, this is technically dy, and then the y going from 1 to 8, and we can see there's the distance that we get. So this integral is the same exact form as this integral. It's just my calculator uses x as the variable, right? But this is really the y that we have. And that's the same numerical value we got before, right? So if I do, let me do second enter, call up the last couple things that I did, call up the last integral. All right, so here was the integral that we got as our first example, and obviously when I hit enter, I get the same value, right? So that shouldn't be surprising because we're finding the length of the same curve, whether we get y as a function of x or x as a function of y. All right, let's take a look at an application. Now, just to give credit where credit is due. All right, again, I want to give credit where credit's due here. This problem is coming out of the calculus book by James Stewart. The version of the book I have is the early transcendentals, the version of the book. So here's a problem number 41 out of the homework section. It says that a hawk is flying at 15 meters per second at an altitude of 180 meters and accidentally drops its prey. The parabolic trajectory of the falling prey is described by this following equation, right? Until it hits the ground, where y is the height above the ground, x is the horizontal distance traveled in meters. So this says calculate the distance traveled by the prey from the time it dropped until the time it hits the ground. So I pulled up Desmos and I graphed this parabola. So here's our parabola, and here's 180 meters. So we're not going to look at negative distance, right? So x is the horizontal distance. So the bird's up here, and the bird is flying at 180 meters. In fact, let me do this. Let's say y equals 180. Right, so here's the bird's path. The bird is flying 180 meters. Right? And then it drops the prey right here. So the prey is going to fall till it hits the ground. So we want to find this length. We want to find the length of this curve. What is the distance it travels? We don't want to look at the distance it traveled horizontally. We want to look at the true distance it traveled along this parabolic path. So that's the arc length. That's the length of this parabola along its path. So if we set up our formula, right? So we know that arc length, the length of that path, is going to be the square root of. All right, now which version of arc length do I use? Do I use the 1 plus dy dx squared version? Do I use that guy? Right? Or do I use the 1 plus dx dy version? Well, in this case, I'm going to use the dy dx, right? So he gave me the equation as y as a function of x. So I'm going to find dy dx right from that form. So I have y equals 180 minus, I'm going to write this as 145 times x squared, right? And then just, I'm just going to use the power rule here. So y prime, right, dy dx, the derivative of a constant is 0, and then I hold off the constant on the other term, take the derivative of x squared. Right? So there's my dy dx. So I have 1 plus, I left off my integral. I have 1 plus, and then I have my dy dx. I have negative 145. Oops, I'm going to go ahead and put the 2 up there. So I have, 2 over 45, and it's negative, and then x, and that all is going to get squared. Right? So there's my integral set up based on that parabolic path that I was given in an equation form. Now, the only other question we really need to answer, right, is what are my limits of integration here? So if I pull my graph back up, right, that's going to be these x limits. Again, I need x limits. Here's dx. I have an x variable, and my integral is the x variable. So I need these x limits of integration that correspond to when it hits the bottom, hits the ground. Now I can see from Desmos that's going to be x equals 90. But let's suppose, on a test, I'm being asked to show the work analytically and not graphically. So keep in mind, when it hits the ground, the y value is 0. So if I come back to my Word document, I'm trying to find where y equals 0. Right? So, what are the x limits of integration? Right? So we already know when x is 0, that's when it's at 180 meters. Right? And then so I want to know when y equals 0. So where does y equal 0 for my equation? So, I would go ahead and take this and add it to the other side. I've got x squared over 45 equals 180. And then I would multiply both sides by 45. And then I would square root both sides. So multiply both sides by 45, and then square root to get rid of the square. And then, without taking out my calculator, I know from the graph that must be 90, and there's my upper limit of integration is the 90. All right, now if we were going to evaluate this integral, this would get pretty nasty, right? And this would be 1 plus basically u squared, and that would involve a trigonometric substitution. So at this point in a textbook, usually what the author will say to you is, we've already put you through the grinder doing techniques of integration. We know you already know how to do trig sub, so let's just go ahead and use the technology to estimate, right? So you can see right here, calculate the distance, it hits the ground, express your answer correct to the nearest tenth of a meter. So let me pause for a second. I'm going to type this in the calculator. All right, actually, let's do this, and I just unpaused, and I haven't typed anything in there. All right, let's go over how we would do this in the calculator again. So we're going to do math, and then I'm going to hit number 9, which is the function integrator. And we're going to type 0. Let me hit my up arrow, and we're going to 90. And then we're going to type in, let's see, the second square root and I have 1 plus, and I'm just going to type in, what I had in that case. So I have negative. Let me use parentheses, all right, to stress what my fraction is, right? Again, I'm looking at negative 2/45 as the coefficient of my x. So I have negative 2 divided by 45. There's the coefficient of my x. And then I need one more parenthesis to finish off my derivative so I can square it. So there's my derivative squared, and then my variable is x. So when I hit enter, there is the decimal approximation. So the length of the curve, i.e. the distance traveled by the prey, is about 209 meters. So our length is approximately 209 meters. All right, so that basically ends conversation on finding the arc length, and this being one of the applications of integration. In the next video, we're going to take a look at surface area.